So let's continue on and talk about cryptography. A couple things we'll talk about is the life cycle, the types, the PKI, that public key infrastructure, some key management practices, not management, but keys, the management of our keys, digital signatures, a little bit about digital rights management, non-repudiation and integrity, and methods of cryptanalytic attacks. So the cryptographic life cycle. Cryptography is great. I've been, telling you all about encryption and what to do and what not to do. And well, it does have a shelf life though, as far as the tools that we have available to us or the algorithms that we have. We get faster processors. The computers that we had 20 years ago, is slower than the watch, slower than your mobile phone now. We get faster processors. We get different types of hardware, different types of software. All that is being developed. We can have the newest, best, fastest computer, and some technology may outrun the cryptography that you're using. Could have more vulnerabilities, lead to coding practices. Somebody may found a weakness in the algorithm. It just takes time, right? So cryptography, these do have a shelf life. They do have a life cycle as far as, is it strong, is it weak, or is it compromised? And when it first comes out and everybody's running it through the mill, right, it's pretty strong. But after time, it can become weak, right? It still works, but it's a weak one. It can, it's just not as good as strong. And then compromised means it's been cracked, right? It's weak. It's not one that we want to really use anymore, but they consider it a compromised algorithm now. So when do we know when it's no good anymore? When should we not use a particular tool or algorithm or cryptography solution? Well, when it comes to hashes, when we have a bunch of collisions. And collisions and hashes is when we're getting the same value for two different pieces of data. And that's not supposed to really happen, right? Everything is supposed to be unique. It happens, though, especially with some of the older hashing algorithms that we've had. Also, when we can have side channel attacks, and we're going to talk about those a little bit later, but those are a couple things that point to weak hashing algorithms anymore, that you may not want to use that particular solution anymore. When it comes to encryption, when we can get information without the key within a reasonable time frame, or when data is accessed by unauthorized people in a reasonable time frame, and within reasonable amounts of money being spent, right? No encryption is really going to be 110% solid. It just takes time to get through whatever it is you're trying to get through sometimes. And it may take 1,000,000 years, and that's a pretty good trade-off. I'll let my data be protected for 1,000,000 years because me and my grandkids and great-grandkids, and we're not going to be here, so it doesn't really matter. So that's why they say within a reasonable time frame. And, it depends on what you consider reasonable. Couple years, that might be pretty reasonable, especially if it's something, a very good algorithm that's protecting some sensitive data, secret data, top secret data through the government or corporations worldwide. Might be worth your time, might be worth your money. So it's kind of an opinion thing, but I would say within a reasonable time frame, if we're talking hundreds or thousands of years, that's not reasonable. Now, the cryptographic types that we need to be aware of, symmetric and asymmetric is a couple ones we need to talk about real quick here. Now, symmetric cryptography, all right, if you think of symmetric, it kind of sounds like same, right? Symmetric, same. These operate with a single cryptographic key. Now, that means we're using that key for both the encryption side and we're using it on the decryption side. So whatever I want to protect, let's say I've got a chunk of data here, and I want to encrypt this before I send it to you so nobody can see it. So I'll encrypt the data with a symmetric key, with a single key, a shared key, or a secret key, a private key, all synonymous. So I can encrypt it and send it over to you. Now, in order for you to see that data, what do you need? The exact same key, right? That's what makes it symmetric. The same key, one key. Now, the problem with symmetric encryption is, okay, I encrypted some data, outstanding. I sent it to you, but you don't have the key yet. How do I get you the key? Key management is the challenge here when it comes to symmetric encryption. How do we keep it secure? You know, I don't want to share it with unauthorized individuals. We don't want somebody else seeing our data. So how am I going to get you the key? Am I going to send it to you in an email? Am I going to call you on the phone? Send it in snail mail? Send it as a carrier? I mean, there's smoke signals, whatever. However, I can get you that key. Now, some of those ways are going to be more secure than others. And I'm actually going to talk about a hybrid cryptography in here in just a second, and I'll show you a very good way to do this. The good thing about symmetric encryption or symmetric cryptography, it is fast. It's very fast in how it operates, and it's cheap to implement. Right? It doesn't take specialized equipment. It doesn't take another infrastructure or anything like that or solution to work. I take an algorithm, the one that I want, symmetrically encrypt it, send it over to you, and however I can get you the key to decrypt it, and you may already have it. Maybe it's something that we shared a long time ago, and that's okay. As long as you keep it secure, and as long as I keep it secure, then our data communications are going to stay secure as well. So some examples of symmetric cryptography. DES, all right, considered weak because it's no longer strong. Triple DES, that was their solution when DES got cracked, so they came up with triple DES. We have the AES, that advanced encryption standard. It's the industry standard now for encryption. We have one called IDEA, Safer, CAST, Blowfish and Twofish, and then an RC4 and RC5. All algorithms. RC4 is one that we've used in wireless in the past. So that's a symmetric encryption, right? You have that pre-shared key, right? So just some good examples here of symmetric cryptography. Now, what about the other side? We've got symmetric. What about asymmetric? All right, if it's asymmetric, that has two keys, a public and a private key, and it has key pairs. So anytime you hear those terms, you need to think asymmetric encryption. Now, this is a little bit newer than symmetric encryption. If you want to compare the two, because symmetric encryption has been around for hundreds and hundreds of years. We haven't had the technical capabilities that we do now, not like AES and the way that they work, like transposition ciphers and things like that. But we've had like a Caesar cipher, right? Hundreds of years old, where, you know, they would take a wooden dowel and a certain length and wrap a piece of leather around it. And then the letters would line up and form a word. And the key was the wooden dowel. They needed to know how big it was, right? Or rotation ciphers, where they would rotate the letters, right? They had that back then too. So cryptography, in that sense, has been around for a long time. Asymmetric cryptography, not quite as long, all right? So, couple examples: RSA, LGML, ECC, the elliptic curve cryptography there. That's actually, I did put a little sentence there for it's the strongest as far as key strength. It's good for wireless. It's good for smart cards. Your mobile phones can use this because it's powerful in how it works, but it doesn't take a lot of power to work. So it's very good for those lightweight devices. And then Diffie-Hellman is also an asymmetric encryption. So remember, asymmetric, we need to think two keys, public, private. There is a pair. They have a relationship. All right, one of them we're going to use to encrypt. The other one we're going to use to decrypt, right? And then hybrid cryptography. I told you I was going to mention this. This is mixing the best of both worlds, the symmetric and the asymmetric. But how do you do that? What are you talking about? Well, what I'm talking about, let's go back to my previous example with symmetric cryptography. If I encrypt something with a symmetric key and I send it to you, you have the encrypted data now, which is part of the goal, but the other part of the goal is for you to read the data, unlock it, right? But you don't have the key. So how can I send it to you securely? I could use asymmetric encryption. I could encrypt the key, the symmetric key, with your public asymmetric key. Now, the only person that should be able to unlock that public one would be your private one. So I'll encrypt it with your public key and send it your way. You will decrypt that with your private key, the key pair, to get the information out of there. And that information happens to be the symmetric key. So now you can take that and apply it to the original data and decrypt the data that way. So that could be seen as hybrid cryptography. Something else we need to talk about is PKI, public key infrastructure. This is also part of asymmetric cryptography, but this leverages all three forms of encryption to provide and manage digital certificates. That's another key term you need to associate with PKI, is digital certificates. Now, a digital certificate is a public key signed with a digital signature. So you get the public key signed by you. That's what ties it to you. Now, digital certificates may be server-based or they could be client-based. Now, if the two are used together, they provide mutual authentication and mutual encryption. And the standard digital certificate format is X.509 right now. Now, these digital certificates, they're part of the infrastructure, the public key infrastructure. And inside there, we have some services that are running, like a certificate authority. So the digital certificates are issued by the certificate authority. That's their job. It oversees the whole PKI infrastructure. So we also may have an RA, or a registration authority. Now, those registration authorities, they work on the CA's behalf. So they verify the identity of the subject, the person, the end user that's trying to access or get a certificate. Now, you may have, depending on your organization size, your CA and RA, may be the exact same entity. If you have a large corporation, let's say global, you may not have certificate authorities at every location. You may only have a couple for your whole enterprise. So you can have a registration authority at each location. And if somebody needs a certificate, you get a new hire. They come in and they verify who you are, forms of ID, however they can authenticate themselves with the RA. The RA says, okay, yes, I believe this is you. And then they can give you a certificate. Usually, in this case, it would be like on a smart card, for example. You know, something else we need to be familiar with is the certificate revocation list, right? You're on the list, the bad list, the CRL. So if a certificate is revoked, I'm trying to think of a reason real quick, like if it was stolen, right? Let's say my smart card, my access card was stolen, right? Somebody stole my wallet and my card was in there. So I would report that, right? I would go to the RA and could report that, and they could send that up to the CA. Now the CA is going to put that key, that certificate, on the revocation list. If that certificate gets put on the revocation list, if whoever stole my wallet now tries to use that card because they may have gotten my PIN number or whatever through social engineering or shoulder surfing or eavesdropping or keylogger, however they obtained it. Once they try to use that certificate, when they do that, the computer is supposed to go look at the CRL, the certificate revocation list. And if it sees that that certificate is now on that list, it won't allow anybody to use that revoked certificate. So the person that stole my wallet would be out of luck as far as using that particular card. Now the CRL is kind of a flat file. It doesn't scale real well, it's being flat. So you may also hear about the Online Certificate Status Protocol, OCSP. And that's kind of a replacement for the CRLs, and it uses a client-server design, and that scales just a little bit better. But regardless, we're looking to see if you're on the bad list. And if you are, you can't use that certificate anymore. Now, something of note, expired certificates don't go on the revocation list. Okay, just revoked ones that have been, if you quit, retired, stolen, something like that, where an administrator goes in and marks that as revoked. So we keep talking about these keys, certificates. Well, certificate authorities, they issue digital certificates, right? We said that just a second ago, and distribute them to certificate holders. You, me, your peers, your coworkers, right? Everybody can get a certificate. Now, the confidentiality and integrity of the holder's private key must be assured during the whole distribution process. So how do we know that the key is going to be secure? Hopefully they're using some type of secure communication between, say, the RA and the CA, because they're going to take that smart card, for example, and put it in a machine so that certificate electronically gets put on there. So public and private key pairs should, used in PKI, should be stored in a central location, and they should be stored extremely secure. If your private key gets compromised and you don't know it, somebody could see the data that's intended for you. They could act like you. We're going to talk about something here in a minute, but as far as digital signatures, they could sign things with your digital signature. And now that could be a bad thing. Somebody could really mess around with you a little bit with that. Now, users, they may lose their private key as easily as they may forget their password. Like you misplace your smart card, well, there goes your private key and your certificate. So a lost private key that's not securely stored means that anything that was encrypted with the matching public key is now lost. I can't decrypt it. So if you send something to me and it's encrypted with my public key, the only thing that can unlock that is the corresponding private key. But if I've lost that, misplaced it, or whatever, I can't see that data now. That's what we're talking about when we say it's lost. I can't unlock the keys, or I can't unlock the data without the right key. So those digital signatures I was alluding to, right? This is used to cryptographically sign documents. We can also sign emails, right? These give us non-repudiation, saying we can't deny that we sent something or can't deny that we did something to that document because it has our digital fingerprint on there now. So digital signatures, they can include authentication of the identity of the signer and proof of the document's integrity. So that means the sender can't later deny signing the document. They can't repute that. Now, how do digital signatures work? Well, they work off your private key, but they hash it. It's not like they send the private key out with the email or out with the document. That would be a little counterproductive. So they actually hash it out and then encrypt it. So if you get it and you hash it and it matches, the hashes match, then you say, oh, okay, it came from Mark, we're good. So everything would be fine. And then we need to talk about DRM, Digital Rights Management. This is a pretty hot topic too. because what you can do is control and protect the content that providers have, and they're trying to give you, their own digital media. It gives them proof of ownership. So, trying to think of a good example here. Let's say I was to write a book and I put it in PDF form. I could put it on the web for everybody to see, but I've protected it with digital rights management. So you have to purchase a key from me in order to access this book. So you buy a key and you download the PDF, all right? You download it on your computer and it's there, perfect. But every time that you access the book, you have to talk back to the DRM server, the digital rights management server, and authenticate yourself. Now, sometimes you can set it up where once you log in, it may be cached on your local machine for 7 days or 3 days or 4 days or 2 weeks. You can decide that on your own for the digital rights management. But you can't read that without the key. That prevents you, for all intents and purposes, of sharing that PDF because I'm protecting my content. That gives me rights to mine. I'm the content provider. So that gives me a sense of protection. You can't email it to somebody. You can't allow somebody else to download it. Now, if you give them your key, then you can. But you can also set up in digital rights management that you can only download it so many times, or it can only be accessed so many devices. There's different ways, and this is not a DRM class, but there are some mechanisms in place that allow you to do that. Now, from the content's point of view, there's 3 key components to its life cycle. The creation of the content, so I write a book, the distribution and upkeep of that content, and use of the content. So how does it work? There's a couple different ways that it works. The way that I described would be an always-on DRM. Have to be on the internet to actually access that, unless the DRM server is in your local network, and then you just have to have local connectivity. But that's not usually the case unless somebody did something inside your organization, inside your infrastructure, and that's the only way you can get the data. But if it's internet-based, right, I don't know you, you don't really know me. If I put something out on my server and you download it through DRM, or download it and it has DRM assigned to it, then you're going to have that key, right? You pay for it or subscription or something like that. You can also have something like a USB key, and it's like a USB thumb drive. If you have the key, you can read the data. So now maybe everybody downloads it, right? You can download the data, but you can't see it until you have the key. You don't have to tie back to the DRM server. You just have to have that key. You plug it in and it will unlock whatever data it is you're trying to look at. And then we can have a digital watermark as well. You know, this used to be on all the printed material. You'd see confidential watermark or private, top secret, for your eyes only, right? Whatever watermark you wanted to put on there. Now we can also have it for audio and video as well. So every once in a while you may, in an audio track, hear something in the background. Or in a video you may see something display across the screen for 3 or 4 minutes, depending on how long the video is. It may be back there permanently, right? So we can watermark our information too, like, you know, evaluation copy or draft or something like that. Now, just a minute ago, we talked about digital signatures and non-repudiation. That means you cannot deny or repudiate having performed some type of transaction. Because we use digital signatures for that, that's how we sign that. Because it's my private key, nobody else is supposed to have that. That is that non-repudiation. So this combines authentication and integrity. So non-repudiation authenticates the identity of the user who performs a transaction and ensures the integrity of the transaction. Because if it was to change, the hash would change. So you would know about the integrity as well. So let's talk about integrity. Integrity is a hash function providing encryption using an algorithm. There's no key. It's a one-way hash, all right? Because there's no way to reverse the encryption. You hash it out and that's it. You get your results. Now, a variable length plain text is hashed into a fixed length hash value, often called a message digest, or you may just hear it called a hash. So what does that mean? Well, you could take the word cat and run it through a hashing algorithm, and depending on whichever one you do, let's say you do an MD5. We're going to talk about that in just a second. I put it through an MD5 hash, and I might get 128 bits out of it. And that's the word cat. Now, if I take the word abracadabra, it's a little bit longer than cat, and I hash that, the value I'm going to get is still going to be 128 bits. It doesn't change. That fixed length value is what we're talking about. So hash functions are primarily used to provide integrity. If the hash of the plain text changes, the plain text itself has changed. One little bit. Even if you went from a lowercase c in the word cat to an uppercase C, the hash would change. One little piece of that changes, and the value that you get will change. I can take it one step further. We can hash out an entire hard drive on a computer. So we'll talk about forensics. That's how they prove the integrity, the trustworthiness of that data upon taking control of it, seizing the data. Because they will take a hash of it and then file it away. But we're not talking about forensics right now. But they can still compare that hash. So when time for litigation comes and they say, well, this is what it was 6 months ago when we seized the drive. This is what it is right now, the day before the trial. You can see the hashes are identical. They did not change. So the evidence is still solid. Same thing with this. If the words don't change, it's solid. We know it proves that integrity. Now, I put a couple different hashing algorithms down there. The SHA hashing algorithm, the secure hashing algorithm, MD5, message digest, and Haval, hash of variable lengths. All right, so SHA, 160, MD5, 128, and then Haval is variable, can go from 128, I want to say up to 160, maybe don't quote me on that one, but it does have some, there's 2 or 3 options in there that you can have, and it's actually a little faster than MD5. SHA and MD5 are almost to that part where people start calling them old hashing technologies, but they're still extremely popular. I see them all over the web when you can download stuff. Right? You get evaluation copies or whatever, and people want to prove that it's okay. You can trust their data, so they'll hash out the value, and you'll see it online. Right? You'll see it on the web page, so you can download it, and you can hash it out too using SHA or whatever, and compare the values to make sure that you're safe, or makes you feel safe anyway. Now, what about some crypto attacks? We got brute force, known plain text, chosen ciphertext, a known key, which is kind of misleading, and side channel attacks. So a brute force attack. I think you're probably very familiar with this one. These have been around for a long time. But a brute force attack generates the entire key space. It is guessing every possible combination, the key to unlock the code. So given enough time, the plain text is going to be recovered. It just sometimes takes time. If your password's very long and it has complexity requirements in there, it may take hundreds, thousands, millions of years. Mine, my passphrase that I use is so long and complex. There's a utility online. I can't remember the website right now off the top of my head, but you could look it up. But I put my password in there, and it told me that through a brute force attack, and you can say so many CPU cycles and things like this, I maxed it out, and it said it would take 14 trillion years to break my password. I feel pretty good about that for somebody to brute force attack my password. So I might not change it very often because of it's going to take a while. We also have a known plain text. This relies on recovering and analyzing a matching plain text and ciphertext pair. So what we're trying to do is get the key that was used, right? So we take somehow we get the ciphertext, sniffing the wire. You know, it's ciphertext. It doesn't mean much to us, and that's okay right this second, because we're going to try to compromise the other machine, right? So I run a man-in-the-middle attack. I get the data. Great. I have some data now. It doesn't mean anything to me just yet, but I've compromised this workstation over here that same data was destined for. They're going to go ahead and decrypt it for me because they have the key. It's awful nice of them. And then I'm going to get the data from their machine. Awesome. So now I know this garbly-gook here means abracadabra over here. So now all I have to do is deduce how we got from here to here, and now I have the key. And now once I have the key, all of that data that you're sending is mine, right? I can see it now because now I have the passcode to get into your data. What about chosen plain text? So a cryptanalysis chooses the plain text to be encrypted in a chosen plain text attack. Again, I'm looking at getting the key. That is my goal. So encrypting without knowing the key is done through an encryption oracle, or a device that encrypts without revealing the key. I can do a chosen ciphertext. Now, this is a mirror of the chosen plain text attack that we just talked about. So the difference is now the cryptanalysis chooses the ciphertext to actually be deciphered. Now, this attack is usually launched against asymmetric crypto systems, where the cryptanalysis may choose public documents to decrypt that are signed or encrypted with that user's public key. And we have also something called a known key. And like I said, it's a little misleading because you may think, well, if I already know the key, why do I have to bother? We don't know all of it. We know something about the key. And we're hoping to reduce the efforts that we have to attack that key or attack the methodology of how you're locking your data. So if the cryptanalysis knows that the key is an uppercase letter and a number only, those characters, we can omit those from the attack. So I know, well, it's all lowercase. I saw them type it. So I know part of the key, right? They never hit the shift. They never hit the caps lock. Or I never saw them hit a number. Or I know I never saw them hit a special character. So we can take that out, right? We can start deducing what the key may be. And then side channel. This uses physical data to break a crypto system, like monitoring the CPU cycles or the power consumption used while it's encrypting or decrypting that particular data. So coming up, next we're going to wrap up Domain 3 by first looking at applying secure principles to site and facility designs.